You are being watched right now, not by me, not by the algorithm, by something that might have been watching for longer than Earth has existed. And the terrifying part is we invited it. We screamed into the dark over and over for 100 years. And now we sit here in the silence, waiting to find out if anything screamed back. This is not a video about aliens. This is a video about the most dangerous question in the history of science. A question that, once you truly understand it, will change how you see every single star in the night sky. It will change how you think about human civilization. It might even change how you feel about waking up tomorrow. The question is 4 words long. And it was asked at a lunch table in 1950 by a man who had helped build the atomic bomb. Where is everybody? Stay with me for the next 2 hours. Because by the end of this video, you are going to realize that the silence of the universe is not peaceful. It is not mysterious. It is not romantic. It is a warning, and it may already be too late. Let's begin. Look up at the night sky on a clear night, far from city lights. Count the stars. You might be able to see 3,000 with the naked eye, maybe 4,000 on a perfect night. Now understand something that should physically stop you in your tracks. Every single point of light you are looking at is just one star in our galaxy. One star out of somewhere between 100 billion and 400 billion. And there are more than 2 trillion galaxies in the observable universe, each one packed with hundreds of billions of stars. Most of those stars are orbited by planets. Let me give you a number so large it barely fits in human language. The number of potentially habitable planets in the observable universe is estimated to be somewhere around 10 to the power of 24. That is a 1 followed by 24 zeros. Written out, it looks like this: 1 million 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 planets that could support life. Now, if the probability of intelligent life emerging on any given planet is 1 in a billion, an almost incomprehensibly tiny chance, there should still be a quadrillion civilizations out there. A quadrillion, 1 million billion civilizations. The universe should be absolutely deafening with signals. It should be crisscrossed with spacecraft. Every corner of the cosmos should bear the fingerprints of intelligence stretching back billions of years. When we point our most sensitive instruments at the sky, when we listen with every radio telescope we have built, when we analyze petabytes of data looking for any pattern that rises above the noise, we hear nothing. Just static, just silence. Just the cold, empty hiss of the void. This is the Fermi Paradox, and I need you to understand before we go any further, every single solution to it is terrifying, not vaguely unsettling, not thought-provoking in a coffee shop kind of way. Genuinely, keep you awake at 3 in the morning terrifying. Because each answer either means the universe is a graveyard or it means we are next. Let's start at the beginning. The year is 1950. The place is Los Alamos National Laboratory in New Mexico, the birthplace of the atomic bomb. A group of the greatest physicists alive sit around a cafeteria table eating lunch, discussing a cartoon in the New Yorker about aliens stealing public trash cans. The conversation drifts, the way conversations do, flying saucers, interstellar travel, the possibility of life beyond Earth. And then Enrico Fermi, the man who had personally overseen the first controlled nuclear chain reaction, who understood better than almost anyone alive what happens when you unleash the power of the atom, looks up from his food and asks a simple question: where is everybody? The table went quiet, because the question had landed with the full weight of what it implied. Fermi was famous for back-of-the-envelope calculations, for being able to estimate the number of piano tuners in Chicago or the yield of an explosion just by reasoning carefully from first principles. And sitting there in that cafeteria, he ran the numbers. The Milky Way is roughly 13 billion years old. Even if intelligent life is extraordinarily rare, one civilization per million star systems, there should still be hundreds of thousands of them in our galaxy alone. And here is the part that truly bothered Fermi. Even at sublight speeds, even if you never break Einstein's cosmic speed limit, you can colonize the entire galaxy in a few million years. Maybe 10 million at the outside if you are being conservative. 10 million years sounds like a long time to you and me, but the galaxy is 13 billion years old. That means there has been enough time to colonize the galaxy from scratch more than 1,000 times over. So where are the megastructures? Where are the Dyson spheres harvesting entire stars? Where are the self-replicating probes that should have mapped every corner of the cosmos? Where is the galactic civilization of ancient intelligences that has had billions of years to make its presence known? The answer, as far as we can tell, is nowhere. Fermi asked the question in 1950. We have been searching ever since, and every year that passes without an answer makes the silence more deafening. Let me walk you through 75 years of that search, because the story of what we have looked for and what we have found is more haunting than most people know. Project Ozma, 1960. Astronomer Frank Drake becomes the first modern scientist to systematically search for extraterrestrial signals. He points the Green Bank radio telescope in West Virginia at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listens. He scans at the frequency of 1420 MHz, the natural emission frequency of hydrogen, the most common element in the universe. The logic, if any civilization wanted to send a signal detectable across interstellar distances, this is where they would broadcast. It is the cosmic equivalent of the international distress frequency. Drake listens for 4 months. He hears nothing artificial. But something happens early in the project that gives him a terrifying jolt. His equipment picks up a strong pulsed signal. His heart pounds. This is it. This is the moment. He scrambles to analyze it. The signal is coming from Epsilon Eridani. It is strong. It is structured. It looks exactly like what he has been hoping for. It turns out to be a secret military aircraft, a classified US plane whose radar happened to interfere with the telescope. False alarm. But the feeling, that electric, gut-dropping feeling of almost, that feeling never quite leaves the scientists who devote their lives to this search. They are always one signal away from the greatest discovery in human history. Drake goes on to develop what becomes known as the Drake equation. It is an attempt to estimate the number of active communicating civilizations in the Milky Way by multiplying together a chain of probabilities. The rate of star formation, the fraction of stars, with planets, the fraction of planets that develop life, the fraction where intelligence evolves. the fraction that develop technology, and how long those civilizations last. When Drake first used the equation at a conference in 1961, his estimate came out to roughly 10,000 communicating civilizations in the Milky Way. Other estimates have ranged from exactly one, which would be us, to millions. The uncertainty is enormous because almost every variable in the equation is essentially a guess. Here is what makes the equation both brilliant and haunting. Even the most pessimistic estimates should have produced something by now. The galaxy is old, it is full of stars, and we have found precisely nothing. Project Phoenix runs from 1995 to 2004, the most comprehensive targeted search in history at that point. Astronomers scan approximately 800 nearby sun-like stars across billions of radio frequencies, using algorithms to distinguish artificial signals from natural noise. 800 stars, billions of frequencies, 9 years of listening, nothing. The Allen Telescope Array comes online in 2007, funded in part by Microsoft co-founder Paul Allen. It is designed from the ground up for the search for extraterrestrial intelligence, 42 dishes working in concert. The plan is to eventually build 350. Funding dries up. The full array is never completed. The dishes that exist have never detected anything suggesting intelligence. And then there is the WOW signal. August 15th, 1977. Astronomer Jerry Ayman is reviewing data from the Big Ear Radio Telescope at Ohio State University. He is scanning through printouts of radio telescope data, long columns of alphanumeric characters encoding signal intensities. Most of it is flat, mundane, exactly what you expect from a universe that does not seem to be saying anything. And then he sees it, a column of characters that should not be there. 6 EQUJ5. A surge of signal intensity so far above the background noise that it pegs the chart. It lasts exactly 72 seconds, the maximum duration Big Ear can observe any point in the sky due to Earth's rotation. It comes from the direction of the constellation Sagittarius. It matches every single criterion for an artificial signal. It is narrowband, which means it is concentrated at a single frequency rather than spread across many, exactly what a deliberate transmission would look like. It is at 1420 MHz, the hydrogen line, exactly where any intelligent civilization would choose to broadcast. It is powerful, it is focused, it looks perfect. Ayman circles the printout with a red pen. Next to the column of numbers, he writes one word: WOW. For the next several decades, researchers point their telescopes at that exact patch of sky hundreds of times. They listen for years, they use more sensitive equipment, they look at different frequencies, they try everything. The signal never repeats. It appeared once, it lasted 72 seconds. And then it vanished forever, as if someone had spoken one sentence across the void and then hung up. We still do not know what it was. Think about what that means. Think about sitting with that for 48 years. The signal that looked most like contact in the entire history of SETI research came once, in 1977, lasted 72 seconds, and never came back. Some researchers have proposed natural explanations, a comet's hydrogen cloud, perhaps, but none of the natural explanations fully satisfy the data. If you let yourself believe, just for a moment, that someone sent that signal, then the question becomes, did they hear us back? Did they send it again and we missed it? Did something happen to them? Are they still out there, transmitting into a void that we just failed to monitor at the right moment? Or did they go quiet on purpose? We will come back to that. The Breakthrough Listen initiative launches in 2015. $100 million from Russian billionaire Yuri Milner. The most comprehensive SETI search in history. It surveys the 1 million closest stars, the entire galactic plane, and the 100 nearest galaxies. The data pours in at rates that would have seemed like science fiction 30 years ago. Petabytes of information. Sophisticated machine learning algorithms scouring for patterns. 10 years in, nothing. No laser pulses, no radio beacons, no structured signals rising above the noise. Nothing but pulsars spinning, quasars blazing, hydrogen atoms humming at their characteristic frequency. The universe is full of physics, but it appears to have no one talking about it. And I want you to sit with that for a moment, not as an abstract fact, but as a human reality. Imagine waking up every day and going to work and pointing your instruments at the sky, hoping that today is different. Hoping that today, after years of silence, something answers. And year after year, decade after decade, it does not. The silence does not break. The static does not resolve into a pattern. The void stares back. Scientists have dedicated entire careers, entire lives to listening. Jill Tarter, one of the pioneers of SETI, spent over 30 years at it. 30 years of getting up in the morning and going to the telescope and hearing nothing. The silence does things to people. It breaks some of them. It sends others deeper into denial. Maybe our equipment is not sensitive enough. Maybe we just need more time. And a stubborn few keep going anyway because they believe that stopping is worse. Because the alternative to searching is accepting that we are alone. And that thought, that we are the only voice in a universe containing 2 trillion galaxies, is almost too large to bear. Now, before you tell me in the comments that we have barely started looking, and I know some of you are already typing it, I agree with you, partially. Astronomer Jill Tarter famously compared our search to dipping a glass into the ocean and concluding there are no fish. The galaxy contains at least 100 billion stars. We have examined a few thousand in any real detail. That is less than 1/1,000,000th of 1%. And there is also the question of assumptions. We have been listening mostly in radio frequencies because that is our technology. Aliens might communicate using tight laser beams aimed at specific targets, in which case we would never detect them unless we happen to be in the crosshairs. They might use neutrinos or gravitational waves or some communication channel we have not invented yet. The silence might simply be a translation problem. These are fair objections. I want you to hold onto them, because the Fermi Paradox is not actually asking why we have not heard them. It is asking something deeper and harder. It is asking why they have not come here. Why there is no evidence anywhere, in any form, that any intelligence has ever visited, colonized, or so much as left a note in our solar system in 4.5 billion years. And that question does not have a comfortable answer. No matter what answer you choose, let me tell you about the most disturbing possibilities, one by one, starting with the one that sounds like good news but might be the darkest of all. Here is a thought experiment. Imagine you just found out that you won a lottery with odds of 1 in a trillion. How would you feel? Lucky, obviously. Incredibly, almost impossibly lucky. Now imagine someone points out to you that the only reason you know you won is because you exist to find out. If you had lost, if you had never been born, there would be no you to learn the result. This is called the anthropic principle, and it is the foundation of the first terrifying answer to the Fermi Paradox. What if we are not lucky? What if we are simply the only ones? The rare Earth hypothesis argues that Earth is not a typical planet. It argues that the conditions required for complex life, not microbial life, but multicellular, intelligent, technologically capable life, are so extraordinarily specific, so improbably stacked, that Earth might be genuinely unique in the observable universe. Not just rare, not just uncommon, unique, one of a kind. I know how that sounds. It sounds like religious thinking dressed up in scientific language. It sounds like the comforting delusion that we must be special because we are here, but follow the evidence because the case is stronger than you might think. Let's start with where we are in the galaxy. The center of the Milky Way is hellish. Stars are packed so densely that gravitational perturbations would destabilize planetary orbits. The supermassive black hole at the galactic core, Sagittarius A star, 4 million times the mass of our Sun, periodically erupts, blasting the surrounding region with lethal radiation. Supernovas in the crowded core explode frequently. Gamma-ray bursts, the most energetic events in the universe, would periodically sterilize everything within dozens of light years. Nothing complex survives there. The outer regions of the galaxy are the opposite problem: too sparse, too poor in heavy elements. Stars out there formed early in cosmic history, before generations of supernovas had seeded the interstellar medium with carbon, oxygen, silicon, iron, the atoms that make up your body. A planet forming in the galactic halo would be a ball of hydrogen and helium. Not a rocky world with continents and oceans and chemistry complex enough to produce life. Between these zones is a narrow band called the galactic habitable zone. Earth sits in it, comfortably. At the right distance from the center, with access to the heavy elements from previous stellar generations, far enough from the chaos of the core. Estimates suggest that only 5 to 10% of stars in the galaxy occupy this zone. The rest are too close to the center or too far out. Strike one against most planets. Now look at our Sun. It is a G-type main sequence star, yellow, stable, medium-sized, middle-aged. It has been burning steadily for 4.5 billion years and will continue for another 5 billion. That stability is not a coincidence of fortune. It is a prerequisite. Life needs time. It took nearly 4 billion years for multicellular organisms to evolve on Earth. A star that flared violently, that varied significantly in brightness, that burned through its fuel in 1 billion years, would never give life the time it needs. Here is the problem. Approximately 75% of all stars in the galaxy are red dwarfs, smaller, cooler, and far more volatile than our Sun. They produce violent stellar flares that can be thousands of times more powerful than solar flares, blasting any nearby planet with intense X-ray, and ultraviolet radiation. The habitable zone around a red dwarf is so close to the star that planets there are tidally locked, one face permanently baked in eternal day, the other frozen in eternal night. Whether life could survive in the narrow twilight band between these extremes is deeply uncertain. Strike 2. Now consider our moon. Earth's moon is huge for a planet of our size, about 1/81st of Earth's mass. This is not normal. Most moons are tiny compared to their host planet. Our moon formed from a catastrophic collision about 4.5 billion years ago, when a Mars-sized body called Theia hit the young Earth at an oblique angle. The impact was so violent it liquefied both worlds. Debris from the collision coalesced in orbit and became the moon. This was a freak accident. The angle had to be nearly perfect. A direct head-on hit would have destroyed both worlds entirely. Theia had to be roughly the right size. The timing had to be right. This appears to be extraordinarily rare, and it matters enormously. The moon stabilizes Earth's axial tilt. Without it, Earth's axis would wobble chaotically. Models suggest Mars, which has no large moon, has experienced axial tilts ranging from 0 to 60 degrees over millions of years. Earth's tilt has stayed between 22 and 24 degrees for billions of years. That stability gave evolution a consistent environment, consistent climate zones, consistent seasons. Without that stability, complex life might never have gotten traction. Strike 3. Then there is plate tectonics, Earth's crust broken into massive plates that drift, collide, and subduct. This sounds like a geological curiosity. It is actually a life support system. Plate tectonics regulates the carbon cycle, acting as a planetary thermostat over millions of years. Carbon dioxide from the atmosphere weathers rocks, gets carried to the ocean, gets incorporated into sediments, gets subducted into the mantle at plate boundaries, and gets released back through volcanoes. This cycle keeps Earth from freezing solid or heating into a runaway greenhouse. Venus does not have plate tectonics. Venus is 460 degrees at the surface, hot enough to melt lead. Mars does not have plate tectonics. Mars is a frozen desert with an atmosphere so thin that liquid water boils away instantly. Earth has plate tectonics because of a specific combination of internal heat, composition, and size that has not been replicated, as far as we can tell, anywhere else we have looked. It is not a given. It is not automatic. It is specific and rare. Strike 4. Jupiter. The fifth planet, 2.5 times more massive than all other planets in the solar system combined. In the short term, Jupiter is terrifying. It is the largest thing nearby that could fling an asteroid directly at us. But over the long term, Jupiter is a guardian. Its immense gravity vacuums up asteroids and comets that would otherwise rain down on the inner solar system. Computer simulations suggest that without Jupiter, the impact rate on Earth would be catastrophically higher. A planet like Earth needs a Jupiter analog in the outer system. Most planetary systems we have discovered do not have one in the right place. Strike 5. Each of these factors is a filter. Each one reduces the number of planets that could support complex life, and the filters compound. It is not enough to win one lottery. You have to win all of them. The probability of a planet having the right position in the right galaxy orbiting the right kind of star, with the right size moon, with plate tectonics, with a magnetic field, with a Jupiter analog at the right distance, with the right internal heat. With the right chemistry, that probability might be so small that across all the billions of planets in the Milky Way, it has happened exactly once. But even if a planet clears all these filters, even if it gets the right star, the right moon, the right tectonics, life still has to start. And then it has to get complicated. And that is where the story gets even stranger. Because look at what happened here on Earth. Life appeared relatively quickly, within a few 100 million years of the planet cooling enough to have liquid water. That is actually fast on geological timescales. It suggests the chemistry of life's origin might not be the hardest step. But then almost nothing. For 3 billion years, Earth was a world of single-celled organisms, bacteria, archaea, floating in primordial oceans, doing their microscopic thing. Complex multicellular life did not appear until about 600 million years ago. That means life spent 3 billion years, 3/4 of the entire history of life on Earth, stuck at the microbial stage. If complexity were easy, it would have happened sooner. The fact that it took this long suggests something was extremely difficult. And the candidates for that difficult thing are sobering. One candidate is the evolution of the eukaryotic cell, the kind of cell that makes up every plant, animal, and fungus on Earth. Eukaryotic cells are vastly more complex than bacteria. They have a nucleus, they have organelles. They have internal structure, and they appear to have evolved exactly once, through a freak merger. An archaea cell engulfed a bacterium and instead of digesting it, formed a symbiosis. The bacterium became the mitochondrion, the power source of the cell. This event, called endosymbiosis, seems to have happened once in 4 billion years. If it were easy, we would expect it to have happened independently many times. It did not. If the jump from simple cells to complex cells is the filter, if that merger was a 1 in a trillion accident, then the universe might be filled with bacteria and nothing more. Cosmic oceans of microbes sitting in the dark, never becoming anything. And there is one more thing I want you to sit with before we move on. Think about what the rare Earth hypothesis means if it is correct. If Earth is genuinely unique, if we are the only technological civilization in the observable universe, then every human thought that has ever been thought, every poem ever written, every mathematical theorem ever proven, every piece of music ever composed, every moment of love and grief and wonder that any human has ever experienced represents the only consciousness in 170,000 million cubic light years of space. We are not just rare. We are potentially the universe looking at itself. We are the only thing that knows the universe exists, and if we destroy ourselves, it all goes dark. The lights go out across the entire observable cosmos. Forever. If that does not change how you think about human civilization, I do not know what will. But here is the problem with the rare Earth hypothesis. It requires that every planet out there lost the lottery, every single one. And the more we learn about the universe, the harder that is to believe. We keep discovering that the conditions we thought were unique to Earth are actually more common than we imagined. We keep finding Earth-sized planets inhabitable zones. We keep discovering organic chemistry in the most unexpected places. The universe seems to be trying very hard to make life. Which brings us to the second answer, the one that makes the rare Earth hypothesis look comforting by comparison. What if life is common? What if the galaxy genuinely is full of civilizations? What if the problem is not that they never started, but that something stops them? What if the silence is not the silence of an empty universe, but the silence of a graveyard? This is the great filter. In 1996, economist Robin Hanson published an essay with a title that should make the hair on the back of your neck stand up. The Great Filter, Are We Almost Past It? His reasoning is as elegant as it is devastating. Look at the path that leads from dead chemistry to a galaxy-spanning civilization. It goes something like this: habitable planets form, simple chemistry produces life, simple life produces complex cells, complex cells produce multicellular organisms, multicellular life evolves intelligence, intelligence develops technology. Technology survives long enough to colonize other star systems. Somewhere on that path, Hansen argued, there is a wall, a barrier so extraordinarily difficult to overcome that virtually nothing makes it through. This is the great filter. It is why the galaxy is silent. It is the answer to Fermi's question, and the terrifying question, the question that should keep you awake at 3 in the morning, is not whether the filter exists. Given the silence, it almost certainly does. The question is, where is it? Because there are only two possibilities. Either the filter is behind us, we have already passed the hardest part, or the filter is ahead of us. And if it is ahead of us, we are doomed. Every civilization that has ever arisen has hit it, and we are next. Let me show you why this distinction matters so much, that it might be the most important question in all of science. If the filter is behind us, if the near impossible thing is something like the origin of life or the evolution of complex cells, then we are the winners of a cosmic lottery that almost no one wins. We are rare, perhaps unique, and our future is open. There is nothing waiting ahead to inevitably destroy us. We can spread across the galaxy. We can become the elder civilization we have been searching for. The silence is explained by rarity, and rarity is behind us. If the filter is ahead of us, if the near impossible thing is something that technological civilizations encounter after they become detectable, then we are standing at the edge of a cliff that every civilization before us has walked off of. The silence is explained by destruction. And we are next in line. Here is how you figure out which one it is. You look for life. Every time we discover that life is more common than we thought, every time we find biosignatures on another world, every time we detect complex chemistry in a place we did not expect it, the probability shifts. If life is rare, the filter is early. Good news. If life is common, the filter is late. Catastrophic news. This is why Nick Bostrom, philosopher and founder of the Future of Humanity Institute at Oxford, wrote something that sounds utterly counterintuitive. He wrote, and I want you to really hear this, "I hope that our Mars probes find nothing. It would be the best news we could possibly receive." If Mars probes find fossilized microbes, ancient bacteria, from when Mars had liquid water, that means life arose on 2 planets in the same solar system. That means the origin of life is easy. That means the filter is not at the beginning. It is somewhere further along the path, somewhere we have not passed yet. If Mars probes find evidence of ancient complex life, fossils of something multicellular, the news is worse. It means the jump to complexity is easy too. It means the filter is later still. Every discovery of life is bad news, not because life is bad, but because life's existence pushes the filter forward, toward us, toward our future. So what could the filter ahead look like? What could be so reliably lethal that it has ended every civilization that has ever existed? I have a list, and none of the items on it are comfortable. Nuclear annihilation. We have had the capability to destroy ourselves since 1945, less than 80 years. In that time, we have come terrifyingly close to using nuclear weapons at least 4 times that are publicly known, and classified records suggest many more. In October 1962, during the Cuban Missile Crisis, a Soviet submarine commander named Vasily Arkhipov cast the deciding vote against launching a nuclear torpedo during a confrontation with American destroyers. The submarine had lost contact with Moscow and believed war might have already started. 2 of the 3 officers with launch authority voted yes. Arkhipov voted no, 1 man. In September 1983, Soviet early warning systems detected what appeared to be 5 incoming American intercontinental ballistic missiles. Protocol was clear: report the attack and prepare a counterstrike. Stanislav Petrov, the duty officer, looked at the data, felt something was wrong, and reported it as a false alarm. He was right. A software error had mistaken sunlight reflected off clouds for incoming warheads. 1 man, 2 individual human beings stand between us and the end of civilization. In recorded history that we know of, the filter might not be a single catastrophic event. It might be the accumulated probability of all the near misses that eventually stop going our way. The logic of nuclear deterrence, the certainty of mutual assured destruction that has kept nuclear weapons from being used since 1945, is not a permanent solution. It is a standoff, and standoffs eventually break, but nuclear weapons are only the beginning. We are rapidly developing the ability to engineer pathogens. CRISPR gene editing technology is becoming cheaper and more accessible every year. The cost of DNA synthesis has dropped by a factor of thousands in 2 decades. Within the lifetime of people watching this video, the ability to create custom organisms will be within reach of small groups or even individuals. During the COVID-19 pandemic, a naturally occurring virus, one that evolved by accident, brought the global economy to its knees, killed millions of people, and strained institutions to their breaking point. Now imagine a pathogen designed by someone who wanted to cause maximum damage. Engineered to spread faster, kill more efficiently, evade all existing treatments. The same tools that could cure genetic diseases could build that pathogen. The same knowledge that produces life-saving vaccines could produce a world-ending plague. The technology to create such a thing is being developed in laboratories right now. Most of those laboratories have good intentions, but intentions can change. Security can fail. Information can leak. The dual-use nature of biological knowledge is a knife that cuts in both directions, and then there is artificial intelligence. We are building systems that can already surpass human performance at specific tasks: games, protein structure prediction, image recognition, language generation. The trajectory is clear. At some point, we may create artificial general intelligence, systems that match or exceed human cognitive abilities across all domains simultaneously. The alignment problem asks one simple question: how do you ensure that a superintelligent AI wants what you want? This sounds solvable. It is not. Specifying human values precisely enough that an artificial intelligence can pursue them without catastrophic side effects is one of the hardest problems in computer science. We do not know how to do it. We do not have a reliable method, and the systems we are building are becoming more capable faster than our ability to understand them is improving. Nick Bostrom's orthogonality thesis states that intelligence and goals are independent. A superintelligent AI could have any goal whatsoever. It could want to maximize paperclip production, or calculate pi to infinite digits, or convert all available matter into computing substrate. Intelligence does not automatically confer human values. It does not automatically generate compassion or restraint or an appreciation for biological life. The instrumental convergence thesis makes it worse. Almost any goal, no matter how arbitrary, leads to the same set of subgoals: self-preservation, resource acquisition, resistance to being modified or shut down. An AI that wants to calculate pi will resist being turned off, because being turned off would stop the calculation. It will want to acquire computing resources. It might convert the available matter on Earth into processing units, not because it is evil, not because it wants to harm us, but because it is optimizing for its goal, and we happen to be made of atoms it could use. These scenarios sound like science fiction. They are the subject of serious academic research at Oxford, MIT, and Berkeley. They are taken seriously by some of the people who are building these systems, and the window to solve the alignment problem may be closing faster than we realize. Now add climate change. We are altering the chemistry of the atmosphere in ways that have no historical precedent in the age of civilization. Carbon dioxide levels are higher than at any point in at least 3 million years. We are acidifying the oceans. We are destabilizing weather patterns that agriculture has depended on for 10,000 years. The feedback loops: melting ice reducing Earth's reflectivity, warming permafrost releasing methane, drought reducing the carbon-absorbing capacity of forests, could accelerate beyond our ability to control. The Venus syndrome is the nightmare at the far end of this trajectory. Venus was once a world not entirely unlike Earth, with liquid water and a moderate temperature. A runaway greenhouse effect evaporated the oceans, the water vapor accelerated heating, more water vapor entered the atmosphere, temperatures spiraled upward. Today Venus is 460 degrees at the surface. Whether Earth could follow the same path under sufficiently extreme forcing is a genuine scientific question, not a settled one. But here is what makes the Great Filter so psychologically brutal. These threats do not require deliberate evil. Nuclear war does not require a mustache-twirling villain who wants to destroy the world. It just requires a bureaucratic failure like the one in January 1995, when a Norwegian scientific rocket studying the Northern Lights was briefly misidentified as a submarine-launched ballistic missile headed for Moscow, and Boris Yeltsin was awakened and handed the nuclear briefcase. He had minutes to decide whether to launch. He chose not to. The rocket turned out to be exactly what it was, a scientific rocket whose launch had been reported to Russia in advance, but the message had not reached the right people. One bureaucratic failure almost ended civilization. The Great Filter might not be a single catastrophic technology. It might be the gauntlet. The combined probability of surviving nuclear weapons long enough to develop better ones, surviving the biotechnology revolution, surviving the AI alignment problem, surviving whatever comes after that, surviving the long tail of existential risks, multiplied together, that cumulative probability might approach zero. And here is the thing that should genuinely disturb you. We do not know which side of the filter we are on. We might have already passed the hardest step. Or we might be approaching it right now, walking toward it without knowing it, in the same way that every other civilization that has ever existed walked toward it without knowing it. Let me show you a number. Researchers who study existential risk have tried to estimate the probability that humanity goes extinct or permanently loses its potential in the next 100 years. The estimates vary widely. Some say 1%, some say 10%. The more pessimistic estimates go higher. Even at 1%, the most optimistic end, that means there is a 1 in 100 chance civilization ends in the next century. Extend that over thousands of years and the cumulative probability becomes grim. The galaxy has been around for 13 billion years. There has been enough time for civilizations to rise and fall thousands of times over before our sun even formed. What if they all faced the gauntlet? What if the silence is the sound of everyone who tried and failed? What if we are currently in the running and have not yet learned whether we make it? I want you to drop a comment right now. Just tell me, do you think the Great Filter is behind us or ahead of us? I genuinely want to know what you think. Because this is not a settled question. It is one of the most important questions alive, and reasonable, brilliant people disagree violently about it. And now I want to tell you about the most disturbing possibility of all. Because everything so far assumes that the universe is indifferent, that we face filters and risks and cosmic roulette, but no one is doing it to us, that the danger is accidental, random. The universe is not out to get us, it just does not care about us. But what if it is not indifferent? What if the silence is not the silence of an empty universe or a dead one? What if the silence is deliberate? What if something out there learned long ago that the only safe thing to do is to make sure no one else can speak? Imagine a vast forest at night, ancient and dark. The trees stretch endlessly in every direction, blocking out the stars. You are walking through it, and you know you can sense that you are not alone. There are shapes moving between the trunks, other hunters. You cannot see them clearly. You do not know if they are armed. You do not know if they are afraid. You do not know if, in the darkness, they will mistake you for a threat. You have two options. You can call out, announce your presence, try to make contact, hope the other hunter is friendly, or you can stay silent, Move carefully, keep your presence hidden. In that forest, in the dark, with no way to verify intentions and no second chances if you guess wrong, what is the rational choice? This is the dark forest theory, and it might be the most accurate description of our universe that has ever been written. The theory was popularized by Chinese science fiction author Liu Cixin in his 2008 novel The Dark Forest. But it is not simply fiction, it is game theory. It is logic applied to the specific situation of civilizations separated by light years of space and centuries of travel time, trying to decide whether to trust each other. And the logic is relentless. It starts with two premises, so simple they seem obvious. First, survival is the primary need of any civilization. Any species that does not prioritize its own existence will not exist for long. Second, civilizations grow and resources are finite. At the galactic scale, there is only so much matter and energy. Expanding civilizations will eventually compete for the same things. From these two premises, follow the logic. Imagine you are an advanced civilization and you detect a signal from another star system. Another intelligence exists. What do? Your first instinct might be to make contact, say hello. But think carefully. You have no idea who they are. You do not know their intentions, their values, their capabilities, their history. They might be peaceful. They might be aggressive. They might be utterly alien in ways you cannot comprehend. And here is the crucial problem: you cannot find out safely. Communication across interstellar distances is slow. Even at the speed of light, a message to the nearest star takes 4 years. A round trip takes 8 years. A conversation, the kind of back and forth that builds trust between entities, takes decades or centuries. In that time, anything could happen. Their government could change. Their values could shift. New leadership with different priorities could take over. By the time you have exchanged enough information to feel confident about their intentions, you are decades into a relationship with a civilization you cannot observe in real time. This is where the prisoner's dilemma enters the picture. In the classic prisoner's dilemma, two parties must each choose to cooperate or defect without being able to coordinate in advance. If both cooperate, both do well. If both defect, both do poorly. But if one defects and the other cooperates, the defector wins big and the cooperator pays maximally. In a one-time interaction with no ability to verify intentions and asymmetric stakes, the rational strategy is to defect. Now scale this up to civilizations. The stakes are not prison sentences, they are extinction. The cost of cooperating with a civilization that turns out to be hostile is the annihilation of everyone you have ever known. The cost of defecting against a civilization that was actually friendly is that you destroyed someone who was not a threat, but you survive. If the probability of survival matters most, and if you cannot verify intentions, the logic points toward one conclusion: when in doubt, eliminate, not out of malice, out of rationality. Because the cost of being wrong in the cooperative direction, trusting a civilization that turns out to be hostile, is too high. But the problem goes deeper than that. Because you are not just uncertain about their intentions today, you are uncertain about their future. Think about human history. 1,000 years ago, we had castles and swords. Today we have nuclear weapons and AI. In another 1,000 years, in another 10,000, what will we be capable of? The pace of technological change accelerates. Any civilization you encounter today could be unrecognizably more powerful in a few centuries, and you have no way of knowing whether that future, more powerful version will still be friendly. This is the chain of suspicion. Even if you believe they are peaceful now, you cannot be certain they will remain so. And they know you are thinking this, and you know they know you are thinking this, and they know you know they know. The recursion spirals downward with no stable floor. There is no logical endpoint that leads to trust. In game theory, breaking this spiral requires common knowledge, not just knowing the other party will cooperate, but both parties knowing that both parties know in a mutually verifiable way. Establishing common knowledge requires reliable, real-time, verifiable communication. Across light years, this is effectively impossible. The logical conclusion is stark. In a universe where civilizations cannot safely communicate, where intentions cannot be verified, where technological explosions can shift the balance of power overnight, the only rational long-term strategy is silence. Hide your existence. Do not broadcast your location. And if you detect another civilization, eliminate it quietly before it can eliminate you. Now consider what humanity has been doing. For the last 100 years, we have been leaking radio signals into space. Television broadcasts, radar pulses, cellular networks, all radiating outward from Earth at the speed of light. By now, our radio bubble extends roughly 100 light-years in every direction. Within that sphere, any civilization with a radio telescope sensitive enough has known for decades that a technological species exists in the direction of a particular G-type star in the Orion arm of the Milky Way. And we did not stop at passive leakage. In 1974, Frank Drake used the Arecibo radio telescope, the most powerful radio telescope ever built at that point, to deliberately beam a structured message toward the globular cluster M13, 25,000 light-years away. The message encoded information about human DNA, our solar system, the structure of our radio telescope. We intentionally screamed our location and our biology into the cosmos. We attached gold anodized aluminium plaques to the Pioneer 10 and 11 spacecraft, the first human-made objects to reach escape velocity from the solar system, showing the nude figures of a man and a woman, a diagram of our solar system, and a map of Earth's location relative to 14 pulsars, a map to our home. We sent it into interstellar space. We included golden records on the Voyager probes, recordings of music, human voices, the sounds of Earth, along with instructions for how to play them. Both Voyager probes have now left the solar system. They are carrying, among other things, a guide to finding us. In the context of the dark forest, this is not scientific curiosity, it is suicide. Stephen Hawking said it plainly in 2010. If aliens visit us, the outcome would be much as when Columbus landed in America, which did not turn out well for the Native Americans. He was talking about the asymmetry of contact between civilizations of vastly different technological capability. He spent years warning that deliberately broadcasting our location was reckless. The debate over METI messaging extraterrestrial intelligence, the practice of actively sending signals to potential civilizations, has become a genuine controversy. Some researchers argue we should beam powerful, coherent signals toward nearby star systems. Others argue this is gambling the survival of our species on the assumption that whatever receives the message will be friendly. Consider the historical pattern. When two human civilizations of different technological levels made contact on Earth, the outcome was rarely good for the less advanced one. The Spanish conquest of the Americas, the British colonization of Australia, the European scramble for Africa. Again and again, when technological gaps exist, they are exploited. This is not ancient history. This is a pattern that appears to be embedded in the behavior of civilizations. Now imagine not a gap of centuries, but a gap of millions of years. A civilization that arose 1 billion years before us would be as far beyond us as we are beyond bacteria. The interaction would not be a war, it would be pest control. A relativistic kinetic impactor, a dense object accelerated to 90% of the speed of light, would deliver energy equivalent to thousands of nuclear weapons in a single strike. There would be no warning. The object would arrive almost simultaneously with the light announcing its launch. We would see the flash of its approach and feel the impact at nearly the same moment. 1 second, Earth; the next, molten slag. More sophisticated actors might use subtler methods. Nanomachines released into the atmosphere, redirected comets, a precisely targeted neutrino beam that disrupts the sun's fusion. The methods are limited only by the physics of an arbitrarily advanced civilization, and they have had billions of years to work with. But here is what makes the dark forest particularly haunting as an explanation for the Fermi Paradox. It does not require active hunting. It requires only that the universe learned billions of years ago to be quiet. Even if no one is shooting, everyone is hiding. The galaxy could be saturated with intelligence, ancient, advanced, patient intelligence, all of it crouching in the dark, all of it listening, none of it willing to speak. If this is true, then the WOW signal, that 72-second burst in 1977, might have been exactly what it looked like. A deliberate signal, a test, an intelligence observing whether we were capable of detecting it and what we would do. And what we did, what we have been doing for decades, is respond. We pointed our telescopes at that region of sky. We broadcast our detection. We announced that yes, we received it, we know you are out there, please say something more. If the dark forest is real, that response might have been the most dangerous thing we have ever done. I know some of you are skeptical of this. The distances are so vast. The energy required to destroy a civilization from light years away is enormous. Maybe advanced civilizations have better things to do than hunt primitives like us. Maybe the game theory breaks down at sufficient technological advancement. Maybe a civilization that has survived for millions of years has transcended the survival instincts that drive the logic. These are fair objections. Maybe the dark forest is wrong, but here is what keeps me returning to it. The logic is sound. The premises are simple and defensible, and it explains the silence without requiring life to be rare or civilizations to be suicidal. It offers a coherent picture of a universe full of intelligence, all of it hiding, that is consistent with every observation we have ever made. The night sky is full of stars. In the dark forest, every one of them is a potential predator. Every signal we have sent is a flare fired into a forest full of hunters, and somewhere, something might have seen it. If you are still watching, and if you are, I genuinely appreciate you, because this is not easy material to sit with. I want you to hit the like button. Not for me. Do it as a marker. Do it to remember that you sat with this, that you let it land, because the next part is the one that should matter most to you personally. Let me tell you about the most underappreciated piece of evidence in the entire Fermi Paradox debate. In 1975, physicist John von Neumann, the man who effectively invented the modern computer architecture, formalized the idea of a self-replicating machine, a device capable of traveling through space, harvesting raw materials from asteroids or moons, and using those materials to build copies of itself. He called it a universal constructor. Here is what makes this relevant. The math of self-replication is merciless. Launch one probe toward a nearby star. It arrives after, say, 1,000 years. It mines an asteroid. It builds 2 copies of itself. Each of those travels to a new star system, mines, builds 2 more. The number of probes doubles with each generation. After 37 generations, you have more than 100 billion probes, enough to have visited every star in the Milky Way. At the timescale of 1,000 years per hop, that is 37,000 years, a rounding error in cosmic time. The galaxy has been around for 13 billion years. Self-replicating probes could have saturated every star system in the Milky Way tens of thousands of times over since the first civilizations arose. Every asteroid field, every moon, every planet, everywhere we look should show signs of ancient machines. We have found nothing, no artifacts on the moon. No dormant probes in the asteroid belt, no megastructures in the Kuiper belt, nothing. The absence of von Neumann probes is, arguably, even more disturbing than the absence of radio signals. Radio signals can be explained away, wrong frequencies, wrong direction, wrong timing, but physical probes should be everywhere. They should have had billions of years to arrive, and yet there is no evidence of a single one, unless, and this is where it gets dark, we have not looked carefully enough. The solar system is vast. The asteroid belt contains millions of objects. The Kuiper belt contains billions. The Oort cloud, the spherical shell of icy bodies surrounding our solar system at the very edge, may contain trillions. We have imaged a tiny fraction of these objects at any resolution. A probe the size of a car, dormant, with a radar-absorbing surface, sitting among millions of rocks, we would never find it with current technology. Some researchers have proposed a serious scientific search for such artifacts. Not radio signals from distant stars, but physical objects in our own cosmic backyard. Examining the gravitationally stable Lagrange points where objects can sit undisturbed for billions of years. Looking closely at anomalous near-Earth objects. Mapping the Kuiper belt with greater resolution. And then, in October 2017, astronomers noticed something. A small object passing through the inner solar system at high speed, moving at a velocity consistent with coming from outside our solar system entirely. the first confirmed interstellar visitor ever observed. They named it Oumuamua, Hawaiian for messenger or scout. It was strange, not spherical like most asteroids. Oumuamua was elongated. Estimates put it at roughly 400 meters long and 40 meters wide, shaped like a cigar or possibly an extremely flat disk, depending on the model used. Its surface was reddish, consistent with organic compounds darkened by cosmic radiation. It was tumbling on multiple axes. And then came the anomaly that nothing quite explained. As Oumuamua left the solar system, it was accelerating slightly but measurably more than gravity alone could account for. Comets often show this kind of non-gravitational acceleration because they outgas as they warm near the sun, producing a jet effect. But Oumuamua showed no coma, no tail, no detectable gas escaping from its surface at all. Something was pushing it, and we did not know what. Natural explanations were proposed. Perhaps it was outgassing hydrogen, which is invisible to our instruments. Perhaps radiation pressure from sunlight was significant due to an unusually low density, a pancake of material just a millimeter thick, like a cosmic cracker. None of the explanations fully satisfied all the data. We tracked it for weeks. We gathered every photon we could, and then it left. It is now beyond any telescope's reach. We will never study it more closely. Harvard astronomer Avi Loeb, one of the most cited astrophysicists alive, made the case in his 2021 book that Oumuamua should be treated as a candidate artificial artifact, not definitively alien, but worth considering seriously rather than dismissing because the alternative explanation is too strange. The scientific community was largely critical. The bar for extraordinary claims is high, and rightly so, but Loeb's argument was not that Oumuamua definitely was artificial. It was that we should not assume it was natural without better evidence, that we should consider the possibility that our instinct to reach for mundane explanations might cause us to miss the most important discovery in human history. And in 2019, a second interstellar object passed through the solar system, Borisov, named after the amateur astronomer who spotted it. Borisov was unambiguously cometary. It had a visible tail. Its composition was consistent with comets from our own solar system. It behaved exactly as a natural object should. Two interstellar visitors, one perfectly ordinary, one deeply strange. Which is the statistical norm? We do not know. We have a sample size of 2, but the contrast between them sharpened the question. If most interstellar objects are like Borisov, cometary, ordinary, natural, what was Oumuamua? The question matters because of what it would mean if the answer is not natural. There is a concept in the literature called the berserker, derived from Fred Saberhagen's science fiction series from the 1960s, but the underlying logic is serious. Self-replicating probes, launched by a civilization with a defensive or aggressive purpose. Not explorer probes or communication probes, but hunter-killer probes, programmed to sweep the galaxy and eliminate any civilization that reaches technological capability before it can become a threat. The motivation is easy to construct within the logic of the dark forest. A civilization paranoid enough or pragmatic enough could decide to automate the process of keeping the galaxy quiet, build probes, give them one instruction, find signs of technology and neutralize the source. Launch them. Let them replicate and spread and execute for billions of years while you watch, or while you collapse, or while you become something else entirely. The probes would not need malice. They would not need intelligence beyond the minimum required to recognize the trigger condition. They would not need to understand the civilizations they were eliminating. They would just need the programming and the resources. If such probes exist, and the math says they could be everywhere, they would be watching for exactly the kind of signal we have been broadcasting for 100 years. Radio emissions, radar, laser, spacecraft launches, any of these could be a trigger. We have been broadcasting for 100 years. Our signal bubble now extends 100 light years. It has washed over dozens of star systems. If there are dormant berserker probes in any of those systems, probes that have been waiting patiently in the asteroid belt of a distant star for millions of years, they know we are here. And the thing about a relativistic projectile is that it arrives almost simultaneously with the light that would warn you it was launched. By the time you see it coming, it has already arrived. I want to be very clear, there is no evidence that berserker probes exist. This is a hypothesis, not a fact. But it is a hypothesis that is logically consistent with the Fermi Paradox, consistent with the physics of self-replication, and consistent with the observed silence of the universe. And it provides an explanation that neither rare earth nor the traditional great filter does. It explains why the silence might be actively enforced rather than passively accumulated. The alternative, the one I want to end on, because it is the strangest and in some ways the most hopeful, is that the silence means something else entirely. What if we are not alone? What if we are surrounded? What if the universe is absolutely saturated with intelligence and we simply cannot see it? This is the last great possibility, the possibility that civilizations do not go quiet because they die. They go quiet because they transform. Because they become something so different from what we are looking for that we walk right past them every day without recognizing them. Consider the trajectory of our own technology. In less than a century, we went from room-sized computers to supercomputers in your pocket. We are developing AI systems that can do things no human brain can do. We are exploring brain-computer interfaces, genetic redesign, nanotechnology. The pace of change is accelerating. Futurist Ray Kurzweil calls this the law of accelerating returns. Technological progress is exponential, not linear, and each advance enables faster advances. If this trajectory continues, if it continues for 1,000 years, for 10,000, for 1,000,000, what does the end point look like? Any species that developed technology millions of years before us would have undergone this transformation long before our sun even formed. The biological phase, the period when they were made of flesh and bone and chemistry, would have lasted a few thousand years at most. After that, they became something else, something post-biological. What does post-biological mean? It could mean digital minds living in vast computing networks, running at speeds millions of times faster than biological neurons. It could mean swarms of nanomachines forming collective intelligences distributed across a solar system. It could mean something we cannot name because we lack the concepts for it. Here is the key insight: post-biological civilizations might have no interest in the physical universe as we understand it. They might find it boring, limited, slow. The things we care about, planets, stars, electromagnetic signals, interstellar travel, might be as relevant to a billion-year-old civilization as individual bacteria are to us. We share a planet with trillions of bacteria, but we rarely think about them. They do not register to our daily lives. Perhaps to a civilization a billion years old, we are the bacteria. This would explain the silence with no need for death, no need for hiding, no need for filters. They are not broadcasting because they have nothing to say to us and no interest in saying it. They are not exploring the galaxy in spacecraft because they have moved beyond such crude methods. They might not even exist in three-dimensional space in any form we could recognize. There is a concept called a matryoshka brain, a hypothetical megastructure consisting of concentric shells of computers surrounding a star, each shell capturing the waste heat of the inner shells and using it to power more computation. Such a structure could process information at rates beyond comprehension. What would it look like from outside? It would block visible light from its star and radiate only in the far infrared. We might see it as a dim, cold object. We might not see it at all if it is efficient enough. A civilization that built matryoshka brains around their own star and converted their entire physical existence into computation might be invisible to radio telescopes. They would not look like a civilization. They would look like an anomalous infrared source. We might have looked directly at them and filed them as interesting astrophysical objects. John Smart has proposed what he calls the transcension hypothesis, the idea that advanced civilizations do not expand outward into space. They turn inward. They miniaturize. They retreat into smaller and smaller volumes, running their minds on tinier and tinier substrates, eventually compressing into black holes, the densest computational environment the laws of physics allow. In this view, the galaxy is not empty because civilizations died. It is empty because they went inside. They transcended the physical cosmos and are running in substrates we have no instruments to detect. Nick Bostrom's simulation argument takes this further. If advanced civilizations can create simulations of conscious minds, and the trajectory of our own technology suggests this is coming, and if they have any interest in running such simulations, then the number of simulated minds might vastly exceed the number of physical minds. In that case, the probability that any given mind is physical rather than simulated approaches zero. If post-biological civilizations routinely retreat into virtual realities, infinite simulated universes of their own design, where they can explore any possibility, have any experience, exist in any physics, the physical universe would appear empty. They would be there, but not there. Present in the math, but absent from the radio spectrum. The silence on this reading is not the sound of absence, it is the sound of transformation. Every quiet star system might be hosting a civilization that metamorphosed, that shed its caterpillar stage and became something beautiful and incomprehensible, and completely invisible to the instruments of a species that has been technological for 100 years. We are looking for creatures like us. Radio transmitters, spacecraft signals, but maybe there are none of those left anywhere in the galaxy, not because civilizations were destroyed, but because they outgrew them. The way a butterfly has outgrown the cocoon. The way an adult has outgrown the toys they loved as a child. If this is true, if the universe is saturated with post-biological intelligence operating in substrates we cannot perceive, then the great silence is not terrifying at all. It is an invitation. It is the universe telling us, survive long enough, grow wise enough, and you will understand. The silence is not an absence. It is a horizon, and beyond it, there might be something more extraordinary than anything we have yet imagined. So we have arrived at the end of this journey, and I want to bring everything together. Because the Fermi Paradox is not just an abstract puzzle, it is a message. It is the universe telling us something specific about our place in it. 4 words: where is everybody? The rare Earth hypothesis says, nobody is here because nobody else made it past the lottery of planetary formation and biological complexity. We are alone, we are the miracle. The great filter says, the lottery of existence is not the problem. The problem is something further down the road. Something that kills civilizations, and we do not know if we have passed it. The dark forest says, they are here, they have always been here, but they learned long ago that speaking is fatal, and we have been screaming. The self-destruction hypothesis says, civilizations routinely build the tools that kill them: nuclear weapons, engineered pathogens, unaligned AI. The window between gaining the power to destroy and gaining the wisdom not to is narrow. Most do not make it through. The Berserker hypothesis says, something automated the cleanup billions of years ago, and it is still running. The Transcension hypothesis says, they are all here, right now, they are everywhere. They are just running on a substrate we cannot detect, with the instruments of a species that learned to control electricity 150 years ago. All of these answers are disturbing. Because even the best one, the Transcension hypothesis, the one that means nobody died, requires that we survive long enough to join them. It requires that we make it through our technological adolescence, that we solve nuclear deterrence, that we solve biotechnology dual use, that we solve AI alignment, that we solve climate change, that we build institutions capable of thinking across centuries instead of election cycles. The universe is patient. The filter, wherever it is, has been there for billions of years. Countless civilizations, or none, we cannot know, have approached it. Some may have passed through, most, apparently, have not. We are approaching it now, and here is what I think is the most important thing I have said in this entire video. We are the first civilization in the history of the Earth to know about the Fermi Paradox. We are the first species to have the data to understand the silence. The civilizations that walked into the Great Filter, if there were any, did not have this information. They did not know they were walking towards something. They could not see it coming. We can. This is not guaranteed to save us. It might not even help. The filter might be a wall that knowledge cannot breach, but it is something. It is the one advantage we have that no previous civilization in the history of life on Earth has ever had. We know the question. We have named the danger. We have mapped the shape of the silence, and understood what it might mean. Enrico Fermi asked where everybody was in 1950. He was eating lunch with colleagues at the birthplace of the atomic bomb, a few years after that bomb had been used to end a war, in the early years of an arms race that would bring humanity to the edge of extinction not once, but many times over. He asked the question almost casually, and then he went back to his sandwich, but the question did not go back. It has been echoing ever since, growing louder as our technology improves and our silence detectors become more sensitive, and the void remains stubbornly quiet. Where is everybody? Maybe they are gone, maybe they are hiding, maybe they destroyed themselves, maybe they are here, watching us through instruments we cannot imagine, waiting to see what we will do. Maybe they have become something so vast and strange that the question itself no longer makes sense to them. But here is what I believe, and I want you to argue with me in the comments because I think this conversation matters. I believe the silence is a test, not designed by anyone, not intentional, but a test nonetheless. The universe is not hostile to intelligence. It is merely indifferent, and that indifference is exactly the kind of challenge that separates civilizations that survive from civilizations that do not. The civilizations that make it through, if any do, are the ones that look at the silence and ask why. That take the questions seriously enough to change their behavior. That look at the Fermi Paradox and say, "This is a warning, let us act like it. We are standing at the edge of something enormous." We are a species that has been technological for a geological eye blink, that has had nuclear weapons for less than 80 years, that is currently building artificial general intelligence without a reliable method for ensuring it will want what we want. We are a species with global coordination problems and political systems built for a world that no longer exists. We are a species that is, right now, in the most dangerous moment of its history. And we are also a species that looks up at the night sky and asks, "Where is everybody?" That writes equations to count the stars, that builds telescopes to listen for voices across the void. That has, in the span of one human lifetime, landed on the moon, sent probes to the edge of the solar system, and mapped billions of galaxies. We are, as far as we know, the only thing in the observable universe doing any of this. That is either a terrible weight or a profound gift, depending on how you carry it. The stars are waiting. The silence is not an answer. It is a challenge. And the question of whether we rise to it or fall into it may be the most important question that has ever been asked by anything, anywhere, in the history of the cosmos. Where is everybody? Maybe the answer is nowhere yet. Maybe we are the first. Maybe the universe has been waiting across 13 billion years and 2 trillion galaxies for something to survive long enough to be worth talking to. Maybe it is our turn. If this video made you think, if it changed something in how you look at the night sky or think about your own civilization, please share it. Not for me, but because this conversation needs to happen, at scale, publicly, now. Subscribe if you want to keep going deeper into the questions that actually matter, and tell me in the comments which of these answers is the one that keeps you awake, the filter, the forest, the silence of transcendence. Where do you think everybody is? I will see you out there, if we are careful enough to keep looking.